Hello everyone, welcome to this video. My name is Amir Senahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate urban heat island in the Earth Engine platform. It's very easy to use and simple programming technique using available functions in the code editor JavaScript language in the Earth Engine platform. Let's go to the Earth Engine code editor environment, and first of all, we need to identify or draw the region of the interest. In this tutorial, I'm going to show you this tutorial actually has two steps. In the first step, I'm going to show you some sort of urban heat island detection using Landsat Images, and also in the second step, I'm going to show you how to do the urban heat island detection using modest night data for the urban heat island in the arid and semi-arid region. So in the first step, I'm gonna select a region in the I'm gonna select the urban area inside the wet areas in Europe or even in the US. No difference which location you are selected. For the first part, as I'm gonna use a day temperature data or daytime temperature data, it is important to select a region surrounded by vegetation cover. For example, in the Europe and in the Russia and also in the northern and also the southern America, you can see that lots of urban areas surrounded by the vegetation cover. For example, for the first part, I'm gonna select the Helsinki as the region of the interest to map the urban heat island in this region using the available tools available here. So, because this city and the other cities in the Finland completely covered by the vegetation cover, and also we have the same situation in the other European countries that you can see in the display. When you want to do urban heat island mapping using daytime or day temperature data, it is important to select a region that is covered by the vegetation cover, because we need clear differences between the urban area and also clear difference of temperature between the urban and the vegetation cover surrounded. But in the arid and semi-arid regions or cases, we have a different scenario that I will show you in the next step. So, in the first, I'm gonna show you how to select your region of interest. For example, I select the Helsinki as the region of the interest, and now to find the province that I have selected here, I'm gonna use FAO administrative borders. Through the search places and datasets, type FAO administrative borders. First layer is available and now imported into the code, and you can see that it is available. So in the next step, I'm gonna show you how to have focus on our study area through the map.center objects. But before that, through the map.add layer, I'm gonna show you the table layer that I have imported into the code. The FAO administrative border is a global product that shows the administrative borders in different levels. Level 1, Level 2, Level 0, and the other levels is also available in the Earth Engine platform. So, as you can see, the southest province in the Finland, including Helsinki, the capital of Finland, is my study area in this tutorial for the first step, and I'm gonna visualize the urban heat islands produced urban heat islands that are created by the urban centers available here, and I want to compare them to see which one has more which one provided more urban heat island or a stronger urban heat island in our study. So in order to select this province, including Helsinki, it's a very simple technique in the Earth Engine platform. Just make a new variable, for example, region of interest equals to, from the input table, including all borders, just filter those of border that are which has overlap with the geometry that's marked on the map as a unique red label. So then through the map.add layer, I want to visualize the selected ROI, and then through the map.center object, I want to have focused on the study area when the code is running. For example, once the code is running, we have focused on the study area, and the only border remained is the southeast border for southeast province in the Finland, in which including the Helsinki as the capital and the most populated region in this country. So in the next step, I need to call Landsat Images. For example, I want to map urban heat island for 2023, and then accordingly I need to call all Landsat 8 images for this year. Make a new variable Landsat equals to, so instead of in the search places and dataset, now you need to call Landsat collection to level 2. Here just type Landsat 8 collection to level 2. Various Landsat collections available in the Earth engine, but Landsat collection to level 2 is unique and providing surface reflectance and surface temperature data. If you had to calculate surface temperature before through different algorithms such as mono window, split window, and the other algorithms such as Planck function, thanks to Landsat collection to level 2 data, you don't need to calculate land surface temperature anymore, and just it is ready and you can call it and use it and apply it into your model. So Landsat collection to level 2 is available here, imported into the code as an image collection, and then I'm assigning image collection to the Landsat here, and for the next step I'm gonna filter out the Landsat images according to the region of interest, and as I'm gonna plot the urban heat island for the year 2003, it is important to use that filter date here. So the filter date including two variables is time start and time end, but these two variables are unknown yet, and now it is necessary to make these before Landsat variable time start equals to the data starting from 2003 and ending to time end ending to 2024, meaning that the all Landsat images for the selected region and 2003 will be called in this code and assigned to the Landsat variable, and then I can select the LSD band for the further process. In order to get information about the available or existing bands in the Landsat variable, go to the USGS Landsat data. In the bands, as you can see, various bands are available, but the main one in this application is band number 3 and number 10, surface temperature band number 10. It is surface temperature data that's including a scale and factor. So I'm selecting the target band here, and then .select is a function helping me to select the desired band in this study. So in the next step, in order to remove the cloudy image, I'm gonna make a new filter according to the cloud properties. So before set a new filter for the cloud, I'm gonna print the Landsat variable, and in the right panel you can see one image collection is under computation and 167 Landsat images available for this region in the 2023. And each image, as you can see, including various properties. And one of the important properties in this step related to the cloud cover percentage. As you can see, the amount of cloud cover by with percent unit mentioned here, and I can filter out the data according to the cloud cover. For example, copy cloud cover property and then make a filter based on. Here I am making a filter Earth engine.filter less than. I'm gonna call those of Landsat data in which cloud cover is less than, for example, 45%. LT cloud cover, call those of images in them the cloud cover is less than 45%. Then run the code and you can see only 89 elements is available now after set the cloud cover percentage. So, and there are the other properties that helping us to do the pre-processing steps to convert the digital numbers to actually the surface temperature for band number 10. As you can see, the scale and factor, there are two properties in the data property that's showing the scale and offset. The offset value through the temperature addition band surface temperature for band number 10 is 149, and also the multiplication or the gain is also its value is available in the data property. So I can write a code, I can write a function that use these two kind of properties and apply them on each available image and calculate the surface reflectance and calculate the surface temperature. The first step for the urban heat island study is actually calculate the surface temperature. But as it is available in the collection 2 data, we only need to call them in the code and apply the scale and offset. That's it, and then we go for the further steps. So I'm gonna make a loop through the function, through the map, in which each input images named as an IMG here, and now I am to extract the gain and offset from the metadata available here. From each input image, through the get, I can extract the value of multiplication for band number 10, as you can see, and I can to convert it to a number through Earth engine.number. Next, making a new variable as offset, same as before, but with a different property, Earth engine.number. From input image, get the addition value. Actually, by this function through the get, I am getting the value assigned to these properties. So the values gathered or collected from the metadata, and now I'm gonna apply the values on each existing bands, on each existing image or element under the image collection. So, and the code is returning for each image that is multiplied to the gain value and added to the offset value that is collected from the properties. So, and now I'm gonna copy all the properties of input images to the outputs. So after doing this, to check the calculation is right or wrong from the syntax perspective, print it again and run the code again. Still 89 elements available. For each date, 1 LSD data is available with Kelvin units that shows the temperature value from, for example, 280 to 320 or 330, but it varies from one location to another location. And also the unit of measurement in this study is not important. You can have land surface temperature in Kelvin or degrees Celsius. It doesn't matter which kind of measurement unit you are using. Just the only thing matter is you must have a land surface temperature band for the calculation. So after making your data, in the next step, I'm gonna make an average image through the median function. So, because for the whole of year, I need one LST image with the lowest cloth cover and also with the most accuracy as I have expected. So I'm making an average image. For example, here is TIRIMG equals to thermal image equals to from Landsat data that is pre-processed well, I'm gonna make a median. You can use the average or median here, but the benefit or advantage of median is that helping us to reduce the impact of extreme or outlier values that's coming from the cloud cover and the other noises during the time series. So in the next step, I'm gonna show you the average temperature image that is created for the region of the interest through the map.add layer. This is TIRIMG, and that is clicked based on the region of the interest, ROI, and then visualization parameter. Leave the visualization empty, and the layer name in the setting is TIR median or the median image. So what is wrong in the code? Invalid JSON doesn't relate relate to actually to the syntax problem into the code, and occasionally the JSON problem happens into your code, and the main way to remove this code is run again and again and again. Invalid JSON not related to the type of programming or the type of data you are using, and sometimes happen during the processing. So just ignore it. So, and then use the false at the end that helping us to avoid automatic visualization for the that highly reduces the speed of processing. Run the code again. Unfortunately, I have a problem in the network and I'm trying to run the code again. You can see the region of the interest, and then I'm gonna show you the thermal infrared images. That is the average temperature image that is created for the Helsinki and surrounded region in the northern Finland, in the southern Finland actually. So I'm waiting for the data to be visualized completely in the image, and during this time we can go to the data setting here and do some sort of enhancement and through the stretching technique if it is loaded completely. Otherwise, we should wait until the final image visualized. So we can test the calculation accurate. We can test the speed of processing through the printing IMG to see that when the average image is created. Now I know that the average image is created, and then I'm clicking on the TIR median. Because of the selected region extent, maybe it's take a little bit time to show the result, but be patient, and also you can also reduce the the extent of border, and also the type of border is very important. Sometimes too many vertex in our study area cause some sort of problem in a speed of processing and also the visualization. For example, if you select your region of interest through the rectangle, maybe you can increase the speed of processing in your work. And also another solution is that generalization or simplification function for the shapefile you are using. For example, here I can do a simplification for the region of interest, and as you can see, the region of interest in this study is a feature collection, and I need to convert it to a geometry first. And for example, if I use dot geometry, As you can see, we have a multi-polygon layer with 300 and 3725 vertices. That shows that shows this layer is very heavy for the processing in the Earth Engine, and we can reduce the complexity of this layer into Earth Engine through some functions available. So here it's very simple technique. After doing filter bound, we need to make a function to apply simplification function on each available actually SHP or on each row available here. So for each SHP, for example, or for each shapefile layer or vector layer, vector is more makes sense because the SHP is a format for vector layer. For each vector, return the vector dot simplify. The simplify, as you can see, simplifies the geometry of the feature with a specific error margin. For example, if I set, for example, 1000 as the error margin value, now you can see the region of interest simpler actually. If I print the geometry, you can see how much simplification is done. For example, when I'm printing geometry, ROI.geometry, now you can see that only we have 131 elements, and with the lower actually vertices, instead of having, for example, more than 1000, or instead of having 3000 vertices in the processing, here only we have 1000. That is very better. So in this area, you can see visualization is done with a higher speed because the complexity is removed from the region of the interest very well through the simplification algorithm. So, and now to see the quality of the final results, just increase the contrast through the stretching techniques available here, and the range of temperature varies from 200, ranging in 200s. So as you can see, the quality of image is very low because the high latitude region always suffer from the cloudy situation, and would be better to set a calendar range actually to bound our data or expands our data into specific months. For example, from the May to September. It's very simple and easy to use technique. Just we can add a calendar range here. After filter date, I'm making a calendar range, Earth Engine that filter that calendar range, 3 arguments available here. I'm gonna filter the data based on the month in the calendar. That's data started from the May to and ends starts from the May and ends to September. And now we have a new thermal infrared images. That's now you can see that. I hope it has higher accuracy and better visualization perspective. Yes, there is, and as you can see, now we have a high quality thermal infrared image or average thermal infrared image with the lowest possible cloud cover in the final image. It's still the loading still is in progress, and until we check the remained area, and after checking the remained area we can go for the further steps. This is a very nice trick because for the Irvan Heat Island, usually the annual data is useful and no need to have high spatial resolution, because the Irvan Heat Island and related changes always occur in the longer time scales, not the short time scales. And most of the time in the studies, people uses the satellite data with 5-year interval or 4-year interval just to visualize the Irvan Heat Island changes. Now the image is ready, and we can go for the further study or further processing in this in the next step. This is a thermal infrared image that and also there are tutorials about the thermal infrared remote sensing, and most of the applications limited to the visible and infrared region of electromagnetic spectrum, and we have less attention to the radar and thermal infrared bands, while they have lots of potential for the further studies and applications. So in the thermal infrared image, what you are seeing related to the temperature of each pixel. For example, the brighter area actually here showing the higher temperature, and the darker region showing the lower temperature. For example, when I select a region or a pixel, the 305 showing the temperature of this pixel according to the Kelvin unit. 305 is the temperature of this pixel, and we can compare different pixels according to the temperature characteristic. But for now, it doesn't have enough information for the airborne heat island monitoring or something like that. To do airborne heat island monitoring with a good accuracy, now we need to do some sort of calculation and use some sort of thermal infrared indices in the Earth Engine platform. So in the next step, I need to get the average value for the average temperature for the region of interest or the selected province here. To get the average value, as you know, the reduced region is a helpful function that enabling us to calculate and extract different statistical operators for the selected region. For example, I'm gonna make a new variable TIR average equals to get TIR IMG, and then throw the reduced region. I will be able to get the average value. The main reducer equals to Earth Engine reducer.mean for the geometry of for the region of interest, that is ROI, and a scale of processing is important, as the Landsat thermal infrared band providing 100 meter spatial resolution. You must set 100 for a scale, and in order to get the value of average, the average value, to get the number of average value instead of its dictionary format, we need to use dot values, and dot gets the first item in the dictionary that is created in the TIR.mean. I'm making a variable, and now you can print the TIR average for TIR average for the region of interest, that is TIR mean. Run the code again. In the console, the TIR, the average temperature value is calculating. It is under computation. Yes, 295 degree Kelvin actually is the average temperature value calculated for the region of interest. And now there is an equation that we can calculate the urban heat island index. Oh, I'm sorry because of the interruption. So make a new variable, urban heat island. The R index equals gonna be calculated here. Urban heat island equals to get from the TIR-IMG dot expression helping us to write an equation based on the thermal infrared image and the average value for the region of interest, equals to, the equation is like this: the TIR image minus, or a subtraction in the here inside the parentheses, we need a subtraction between the TIR image, the average value that is calculated, and the result should be divided to the average value again. that is the calculation for the index, and my main reference for this calculation is the paper I'm showing you here. Actually, the index I'm gonna to calculate is UTF-VI, that's coming from the differences between TS, the temperature image, the differences between temperature image and also the average for the region of interest over to the average of temperature. And this paper is very useful for the urban heat island detection, and as you can see, the full name of each indices completely shown here: urban thermal field variance index. That is one of the main applicable indices that we can use for the urban heat island detection. You can use this paper as a reference, and yes, we're gonna do calculation based on, and also there is a table here that's showing that how we can actually define different categories and different classes based on the thermal infrared variance over the urban heat island created by the cities in different classes. That is very helpful technique, and also very helpful references that I'm suggesting to use this reference for your own studies. So, and also maybe there are the others indices in this regard, but you are free to use any other algorithm you want to use. But in my experience, I found this method very useful for the urban heat island, so that's my option for the calculation. But for the other works and also for your projects, it's completely up to you. You can have more literature review, and also I'm totally open if you have more newer or a better indices for the urban heat island detection. So, and back to the calculations. So as you can see here, the TIR and mean both are unknown variables, and now I want to define the TIR and average. The TIR should be equals to the TIR IMG, and the mean equals to TIR mean, that is calculated before like this, and I'm renaming this file as urban heat island index UHI. And now in the next part, through the map.add layer, you can visualize the urban heat island the calculated index for the urban heat island. So UHI, that is clipped based on the region of interest, and then we can make a palette for this part, and also, but let's no need to make a palette for this part, and leave the palette and visualization empty, and the name is the layer name will be UHI, and use the false at the end. Run the code, and now the UHI image is created, and you can see the result now. So increase the contrast through the stretching techniques, and as you can see, some regions in our study completely highlighted because they have more temperature variance compared to the rest of the region in our studies. And most of the time, these regions actually have correlation with the urban structures or non-vegetated covers in our study, as you can see. But now, to get more insight about the urban thermal variations, or to get more insight about the thermal variations regarding to the urban heat island, I want to classify this image according to the thresholds available in the paper to different classes, the weak UTF-I to strongest one. So it's very simple and easy to use techniques in the Earth engine. This classification gives a very useful insights to interpret the output values coming from this index. So now I'm making a new variable as urban heat island classes. Class equals to, now in the first step, before define this condition, I need to make a new image, a constant image, actually, earthengine.image.constant, that including all pixels as 0. And then through that where I will be able to add new values or new classes or according to the conditions available in table number 2. So the first class is class week. The values from 0 to this value in the UTF-VI range or the UHI image we have here. So in the constant image, those of pixels through the where, those of pixels in which the UHI.GTE greater than or greater than equal 0, and those of pixels in which Irvine Heat Island index value that less than this value 0.005. So label them with number 1. So this is the first condition or first class. So to add more classes, use that where again. That where. So this time, those of pixels, the second condition. The second condition is middle class. The values in this range. So this is class week. So those of pixels in which Irvine Heat Island value is greater than 0.005 and those of pixels in which Irvine Heat Island .lt less than 0.01, so equals to number 2 or class number 2 or class that labeled with middle. So the next condition that where in the UHI image the pixels greater than 0.010 and pixels in UHI that are less than, so for the strong class 0.015 will have label number 3. This is a strong class. Oh yes, this is a strong class. And the next condition that where in the Irvine Heat Island image the pixels greater equal 0.015 that and Irvine Heat Island is less than, so 0.020 equals to class number 5, the stronger thermal variance, showing the stronger thermal variance related to the study area. And the last condition, including those of pixels in which Irvine Heat Island is greater than, so as you can see, greater than the 0.020, greater equal this value, and the rest of them it doesn't matter, and the final label is label number 5. These are strongest actually thermal variance regarding to the Irvine Heat Island that is detected. So now I'm gonna visualize the output for this part through the map.add layer, actually the popular technique or the visualization in the Google Earth Engine platform. UHI class, I want to visualize UHI class that is clipped based on the region of the interest, that clip region of the interest, and also the visualization properties here is very important. The starting point is 1 and the ending point is number 5. The minimum value 1 and the maximum value is 5. We have 5 classes here and we need 5 color palettes. So here another argument is palette equals to, so you can use any palette color you want. It's totally color palette you want. It totally depends on you. And also I don't have any standard for the urban heat island color table or something like that. So the palette equals to, for example, from the white, yellow, orange, red, and brown. This is my color palette for the urban heat island. You can use it, or you can use what you have, or you can use any color palettes available in the papers. It's totally up to you. So, and the next is the layer name. The layer name is UHI class, and use the false at the end. Run the code again, and now urban heat island class is uploading here. So as you can see, we have urban heat island with 5 class, 1, 2, 3, 4, 5. Yes, as you can see, there are some regions with actually red color and brown color that shows the higher temperature variance in the study areas. So most of the red regions completely matched with the urban centers, or some of them might be because of the bare lands available in our study area. In order to have more focus on the urban area, as you can see, for example, this city completely showing a hotspot here, and also the Helsinki and Espoo, the most populated region, shows the highest values, and also all the urban cities or residential areas showing higher variances. But now, in order to have focus on the study area, we can remove non-urban regions in the calculations. It's very simple and easy to use technique. So in order to remove the non-urban regions, so I'm gonna use a dynamic world land cover layer with 10 meter spatial resolution. So in the previous tutorial in my YouTube channel, the tutorial about the dynamic world product is available. You can use that for your own studies, and also you can try it very well. So the dynamic world version number 1 is available here. Just here I'm making a new variable as urban. I want to select the urban area in the land cover map. So the land cover layer is image number 2, Google Dynamic World. This is developed by the Google experts. That is one of the best and awesome land cover products I've ever seen in my career. So image collection number 2, that should be spanned to a specific period of time, same as the thermal infrared data, that filter date, spanning the data from time start to time end. And then we have to bound our data according to the region of the interest. So after doing this, I can use the calendar range, same as what I have used for the Landsat, like that. And then for the next part, I want to make a mod image. Actually, the mod find or calculate the frequent classes in each pixels for the region of interest. And then the target band in this product, as you can see in the product, it has 10 meter, including various actually classes. You need to select the label layer because it is including all classes collectively together. So now select the label, and built or urban area is class number 6. Dot select, I'm using the dot select here to select the target band, and then dot equals helping me to find the urban regions very well. Now I have a binary image 0 and 1, in which number 1 showing the urban area. Through the map.add layer, I can show you what it is included. So urban dot clip based on the ROI, the visualization empty, and the name is urban, and use the false at the end. Run the code again, and now as you can see, urban heat island urban actually is ready. That only shows the urban infrastructure or urban facilities, and now I can mask out the data, the non-urban pixels for the further computation, because I want to have information about the urban heat island, and non-urban pixels should be removed from the calculation. So here, as you can see, in the map.add layer, or in the map.add layer, or in the final step here, we can add something new. So here, dot update mask. So according to the urban layer, urban. Run the code. So urban, oh yes, it is wrong. The urban is right. Code is running, invalid JSON. Run the code again. Once the process is done, check urban heat island class on, and now you can see the variations or thermal variations of urban heat island in your region of interest very well. So the darker regions showing the higher variations, and also the brighter regions showing the lower variations. So, and now you can use this code for different places or different urban areas that's surrounded by the vegetation cover. For example, in the geometry, as you can see, I can select another region, delete the geometry, and select another region. For example, I'm gonna select a region in the Germany. For example, a big city is Berlin. Yes, the capital of Germany. And now I'm selecting Germany based on. No need to save the code, but you can save it for your own. And now this is the Berlin layer, that province including Berlin. The urban heat island class is available here, and showing the thermal variance over the Berlin city, and shows that in which areas or for which regions urban heat island could be stronger. So by different colors, it's very useful. And for some of the regions that less suffer from the cloudy situation, you can increase the range of the calendar from the first month to the month number 12. It's totally up to you. So yes, this is a technique that you can use it for the urban heat island detection for your study area. It is very, very helpful tutorial for the urban heat island monitoring for your studies, and also I highly recommend you to use this to get more insight about the temperature thermal characteristic of or thermal emissions in your urban area. For example, for Paris, we can run the code again. This is the region of the interest, and urban heat island class Yes, you can see the urban heat island class for the all residential area that is detected in this image. That is very useful. And in order to save the final result, use that export that image to drive. So some arguments should be considered in this regard. One of them is the image equals to urban heat island classes that is clicked based on the region of interest. The description is the name of the output layer. It is urban heat island layer, and a scale of data should be 100 because Landsat temperature data has 100 meter spatial resolution. And the next thing that is important is the region of interest, that is ROI. The CRS, the coordinate system, equals to EPSG 4326. And the next one is the maximum pixels that you can get export 1E13 should be, and the output folder, the main folder that you want to save your data on, could be anything, or you can set different names or make different folders in this regard. So that's it. And now, for example, in Paris, I'm extending the month from the January to December, and then I'm running the code to use all existing images during a year for the urban heat island detection in the region of interest. So this is UHI image class that is created. Sometimes the noises because of the cloud cover or something like that occurred in the processing. We can increase the rate of cloud cover. We can select those of images with the lowest cloud cover in the computations to get much better images for the outputs. As you can see, it has lower noises, but to remove the all existing noises, still I'm suggesting to increase the temporal period. For example, select 2 years for the making a map. That would be very helpful to reduce the actually impacts of the cloud cover and noises in the calculations. So in the task, the final image is also available. You can click on run, and then the process of saving the final result in the Google Drive started. And once the tab layer color turned to the blue, meaning that the process of saving is completed and successful, and you can pick it up from the Google Drive and use it in your own desktop softwares. I hope you like this tutorial, but there is a second part in this tutorial that will be published in my YouTube channel that's showing you how we can calculate the urban heat island for the arid and semi-arid region using MODIS images. So if you have any question or problem regarding this code, the code link for me is my code is also available below the video description, in the description box, and you can use it and compare yours with mine. If still there is any problem, you can reach me out through my YouTube channel. Thank you for your attention.